Hello, welcome back to the online courses on formal languages and automatic theory. Today I will talk about a very, I would say, involved thing about undecidability and semi-decidability. So these are called Rice's theorems. Actually, this Rice's theorem has two parts. We will cover the first part in the first lecture and the second part in the second lecture. So this essentially proves that almost everything that we can talk about for Turing machines is undecidable, and certain things are not even Turing recognizable. Okay, so before going to the details, let me first introduce a very important concept about recursively enumerable languages, namely properties. So I will define by this RE, capital RE, the set of all languages accepted by Turing machines. So language of M such that M is a Turing machine. So it's basically the class of all RE languages or recursively enumerable languages. A property of recursively enumerable languages is nothing but a map P from this set to the set true or false. Okay. So these properties are properties pertaining to recursively enumerable languages. So it's a map from this set to the true-false set. Okay. It's not a property of Turing machines. I will come to that very shortly. So for example, emptiness is a property. So we know that the empty language is finite, context-free, regular, everything, including recursively enumerable. So phi is a member of this RE, and if L is empty, then for this the property is satisfied. And if you take any recursively enumerable language which is not empty, for that this property is false. Yeah, so the next question is, even definition of RE sets includes Turing machines, because without Turing machines we cannot define their languages. Of course, we can have other alternative ways of specifying recursively enumerable languages, but in this context we will use Turing machine to define a recursively enumerable language, like the language of M. So, properties are also therefore specified by Turing machines, although properties pertain to RE languages, not Turing machines. Okay. So, but we do not have any other, I would say, weapon to define a property. So, properties too are specified by Turing machines. And for example, I can specify this property, emptiness property, by any Turing machine whose language is empty. Okay. So the emptiness property is specified by any Turing machine, any member of this set, PM, M, such that the language of that machine is empty. Fine. So apparently there are no easier ways of specifying properties. They pertain to RE sets, and for every RE set there will be multiple Turing machines accepting the same language. We pick any of this and talk about that machine standing for this entire property class PM. Okay. So here are some other important examples. Finiteness property. So it is specified by a Turing machine, any Turing machine whose language is finite. Likewise, I have regularness or regularity property. So it is specified by any Turing machine whose language is regular. Fine. Likewise, we have context-free property. This is specified by any Turing machine M whose language is context-free. Likewise, we have recursiveness property or other things. And here is another example, acceptance of a string. Any member of a Turing machine N such that 0, 1, 0, 1, 1, 0, 0, 0, this is in the language of N. So the property is that it is true if and only if that RE language contains the string, it is false if it does not contain the string. Okay. So this is another property. Another property is fullness property, for example. So that is specified by any Turing machine M whose language is the entire of sigma star. Okay. So these are all properties of recursively enumerable languages, each specified by a representative Turing machine. One thing that you must understand now, specify a property by a single Turing machine whose language has that property. Okay, having that property, it's not exactly Turing machines having any property. The language of that single Turing machine that we use as the representative should have that property. And once again, this point highlights that properties are properties of RE sets, not of Turing machines. Therefore, what is important is that a property must be independent of the machine that we use to represent that property. Okay. So, to understand the difference between Turing machines and recursively enumerable sets in terms of properties, here are some non-examples of properties. And I will explain why these are not examples. Okay. Let us consider this. Any member of the set of Turing machines such that M has at least 20 states. Why is this not a property of RE languages? It's a property of Turing machines, not of RE languages. Let us see why. Consider, for example, the RE set empty. Okay, phi is a finite set. Eventually, it is recursively enumerable in particular. And we can design two Turing machines, M1 and M2, both accept this empty set. So, but I can design M1 and M2 in two different ways, although both accept the same language, namely they accept nothing. Okay. So, for example, I can design a Turing machine M1 that irrespective of the input immediately jumps from the start state to the reject state and halts. Definitely you require only two states here. Of course, there should be an accept state, so only three states are needed. So M1 has only three states. In particular, 3 is less than 20. On the other hand, I can design another Turing machine M2 which has more than 20 or at least 20 states. For example, M2 can do something like this. It starts at state S, goes to a next state, and the next step symbol, another state, another state, another state, another state, another state. Maybe it does this for 3000 number of times. So there are 3000 states. After that, that machine simply loops on that 3000th state, simply moving forward. So it rejects everything implicitly, but for some reason we have designed it in such a way that it has 3000 or 3001 states. Okay. Definitely, M1 and M2 both accept phi, empty set. This has less than 20 states, whereas M2 has 20 or more states. In fact, M2 can be more, I would say, serious than that stupid machine that I talked about just now. For example, maybe it is trying to solve a puzzle. If it can solve the puzzle, it accepts its input. For example, and let's assume that this puzzle is not solvable. For example, M2 may be trying to find out a Pythagorean triple, a comma b comma c, a square plus b square equal to c square, such that A, B, C are all odd numbers. We know it's impossible to find it. Okay. Because if A is odd, A square is odd, B is odd, B square is odd. If you add them up, C square has to be even. And therefore C has to be even. Of course we know odd even case is not possible. Only possibilities are odd, even, odd, or even. Anyway, so if the machine is solving some such puzzle, or even something much harder than this, which is unsolvable, then it can never solve the puzzle and can never accept whatever its input is, and therefore the language of M2 is also phi, empty set. Okay. But the problem is that if you represent phi by this Turing machine M1, since this has less than 2020 state, this property is false, at least 2020 states, this is required. So this property is false if phi is represented by M1. On the contrary, if phi is represented by M2, this property is true, because M2 has at least 2020 states. Okay. So the number of states is actually a very private property of Turing machines. They are not exactly properties of RE languages. Let us look at some other example for clarifying this idea. Any member of M such that M is a total Turing machine. Once again, being total or not is sometimes a choice of the Turing machine. Take any recursive language. Phi, for example, sigma star, for example, anything which is recursive, therefore I know that a total Turing machine accepts that. Okay. However, from that total Turing machine, I can construct a Turing machine by adding a new reject state, as that whenever that total Turing machine goes to that old reject state, it keeps on looping in that state without ever going to the new reject state R prime. So you see that being total is for recursive languages, being total is often or maybe always a choice of the Turing machine that implements or recognizes or decides that language. So, total Turing machine, being a total Turing machine is not a property of RE languages. It's a property of Turing machines. Similarly, you see, any member of M rejects this and halts. So once again, rejection of this implicitly or explicitly or by forcibly going to a loop is a choice of this Turing machine. Therefore, this cannot be a property of RE sets. It's a property of Turing machines in general. Okay, any member of M such that M never goes to the or ever goes to the right of the input or never, whatever. So, for example, if I take a context sensitive language, then I know that a linear bounded automaton can accept it, which is like a Turing machine, but it never happens to go outside its input area. Okay. But another Turing machine I can definitely design that accepts the same context sensitive language by just moving one step further to the, one step past the input. Okay. So this is once again a property of Turing machines, not of RE sets. This is yet a fifth example. Any member of any Turing machine that has the smallest number of states among all machines accepting its language. Okay. Fine. So these are non-examples. Then why properties are important? In order to understand, we have to define two types of properties. Okay. Trivial property, you recall that a property is nothing but a map from the set of all recursively enumerable sets to true, false, this set. Okay. So, there are two maps which are the constant maps T and F. Okay. These are called trivial properties. Okay. The constant map Re to T, F, taking any recursively enumerable language L to T, this is the constant map T, this is called trivial. Likewise, the constant map taking every language to the false thing, so no language here, of course, this map means that every L in Re satisfies that property, and here this says that no recursively enumerable language satisfies this property. Okay, these are called trivial property. Any other property is called non-trivial. Okay, not trivial is non-trivial. So, example of trivial property, the language of M is recursively enumerable. This is true for any Turing machine and any recursively enumerable language. Therefore, this is trivially true for all recursively enumerable languages. Okay. And its complement, that is, no L is recursively enumerable, is a trivially false property. And here is a non-trivial property. The language of M is recursive. This is not universally true. There are languages that are recursive. That is, for this language, this property is true. There are languages like the halting problem or the membership problem, which are not recursive but recursively enumerable. So this property is not universally true. True sometimes, false sometimes, some other times. Okay. Now, okay. And there is a second type of property, monotonicity. Okay. This basically says that if a property is called monotone, if some L satisfies that property, then any superset of L prime, which also happens to be recursively enumerable, must satisfy that property too. Okay. So, for that matter, we can represent f by 0, t by 1. So, f is less than equal to t. And then this property, as I mentioned, this can be written as if A and B are two recursively enumerable sets, A is a subset of B, then property of A must be less than equal to property of B. That means only possibilities are false less than equal to false, false less than equal to true, or true less than equal to true. So, if it is already true for A, take any superset of A, that property can never become false. Fine. So, this essentially says like that. And a property which is not monotone is definitely non-monotone. And here are some examples. Monotone properties. Lm is infinite. So, that means that if I take L equal to language of some M, if that is infinite, then any superset of that infinite set is also infinite. Likewise, if L of M is sigma star, then any superset of sigma star but subset of sigma star, because all languages are subset of sigma star, must be sigma star also. So, these are monotone properties. Non-monotone properties are like this. Lm is finite. For example, the empty set is finite, but sigma star, empty set is finite, so this is true for the empty set, whereas sigma star is infinite. And so, this is empty set contained in sigma star. This property is true for the empty set, false for sigma star. This violates this. Okay. Likewise, L of M is empty. Basically, the same argument shows that these are non-monotone properties. Okay. Having seen these basic definitions, let me now state and prove Rice's theorem. Actually, this theorem comes in two parts, part 1 and part 2. Part 1 is actually called the Rice's theorem, but for removing ambiguities, we will always mention this is Rice's theorem part 1, this is Rice's theorem part 2. If nothing is mentioned, we imply part 1. Rice's theorem means Rice's theorem part 1. Okay. Now, this is a very surprising theorem. So, once again, look at these trivial properties. Any property that is not universally true or not universally false is a non-trivial property. Now, this says that Rice's theorem part 1 says that any non-trivial property of RE languages is undecidable. So what does it mean? It means that if I make a collection of all the Turing machines such that their languages satisfy this property, this set, so this is a collection of Turing machines such that the property is satisfied by the language of n, equal to 2 is satisfied by true. This pi is not a recursive set. So any RE language, any non-trivial property of RE languages, all the examples that we have seen, like being empty, being full, being recursive, acceptance of 0, 1, 0, 1, 1, blah, 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 something. Okay. These are all non-trivial properties because they are not universally true or not universally false. These are all undecidable. Okay. So this is quite a very powerful and strong statement about recursively enumerable languages. Proof is not really that difficult. We use reduction from the halting problem. Okay, so this proof requires some little bit of background. Before jumping to the proof, we make some notes. So let P be a non-trivial property of recursively enumerable languages. Suppose that L of P of phi is false. You can actually handle the other case very analogously. Okay, so you can try thinking about this. Why? This assumption is not a very bad assumption. This can be handled very analogously. Okay. So assume that this property is not satisfied by the empty set, which is recursively enumerable. But since P is given to be a non-trivial property, it cannot be universally false. So there must exist some recursively enumerable language L such that P of L is true. And definitely L is not equal to empty set because P of empty set is false. Okay. P is non-trivial, it cannot be universally false, so there must exist some recursively enumerable language which satisfies the property P. And if this was true, then you should take some L such that P of L is false. Okay, but we will take this case. Here false, here it is true. Just by swapping T and F does not matter actually. Okay. Since P is non-trivial, there exists L which is not satisfying property P. Okay. Now L is a recursively enumerable language and therefore it must be accepted by at least some Turing machine. Let us call that Turing machine K. So let K be a Turing machine whose language is this L which satisfies property P. Fine. So now we are in a position to propose or explain or illustrate a reduction from the halting problem to this set, HP to this set. Recall of this, P of empty set is false, P of L is T, and L is accepted by a Turing machine K. Okay, maybe total, maybe not, we don't care. Some Turing machine K. Fine. Now the steps of the reduction. Halting problem to pi. So once again, let me highlight that a reduction has the only job of converting an instance of this to an instance of this. So an instance of halting problem is a pair of a Turing machine followed by an input for that machine, m, w, which can be written as m hash w in the encoding scheme of a Turing machine. Okay. On the contrary, if you look at this pi, this language, its members are n, Turing machines. Okay. So this reduction should output a Turing machine n. Since this has to be a meaningful reduction, it must be that language of n is true, it satisfies the property P, that is P of L of n is true, if and only if M halts on W. So that is the correct reduction. Okay. If we have a reduction, then since we know that the halting problem does not have a decider, the decider of y will produce a contradiction. Okay. So once again, in all reduction examples, a Turing machine, total Turing machine is in action. Given this input, it will produce a Turing machine n. So you convince yourself how this conversion can be made. But if I want to build something from something, I must tell how this final product will look like. And then you convince yourself that this final product can be prepared from the raw material. Okay. Again, you should say the behavior of n on input V. Okay. N will simulate M on W, not the reduction Turing machine. It ends by creating a Turing machine having the behavior as I am going to explain now. Okay. Fine. So how does n behave? Copy its private input V. So W is the input of M, V is the input of N, and the reduction engine will not assume any input V. It will work for any input V. Okay. The only thing it will generate is N. But since N is a Turing machine in its own right, it requires a private input V. Okay. So now N copies V to a separate tape, maybe a second tape, and since the Turing machine that makes the conversion knows M and W, it can embed this finite amount of information in the finite control of M. So from that finite control, N copies M, or rather W, to its first tape and simulate N on W. Okay. Then what happens, if the simulation halts, then that simulation has anyway halt, then this machine goes. Well, you recall that this proof requires another Turing machine K, whose language is L, such that P of L is true. So that is again a constant machine. Okay. It is irrespective of this M, W and an input of V. It's a constant machine, depending upon your choice. This K and this language. It's any constant language you choose. As that P of L is true and K is a machine to accept L. Okay. It's a constant machine. Fine. So this, I would say, the description of K can also be embedded in the finite control of the target machine N. So if the simulation halts, what N does, it simulates K on V, maybe on its second tape, or maybe copying back that content V from the second tape to the first tape, doesn't matter. But it requires somewhere to store this V, because it can be an arbitrarily large thing. Simulate K on V, and if that simulation halts, if that simulation accepts, reject, loops, loop. This is the simulation. Accept if and only if K accepts. If K rejects explicitly, reject explicitly. If K loops on V, this simulation also loops on V. So now let us see that our desire of producing a machine N, which satisfies this, its language is true, satisfies the property P if and only if M halts on W, this property is satisfied. Okay. So why? Suppose that M actually halts on W. So that means the machine, the simulation of M by N will eventually halt, and N will get the chance to come to this third step, right? That is its simulation of K on V. Okay. And if K accepts, it accepts. If K rejects implicitly or explicitly, N also does the very similar thing. So if M halts on W, N accepts if and only if K accepts. Okay. So be aware of N on input V. This V is actually used as an input to that Turing machine K. So M halts on W implies N and K have precisely the same language, namely L. Okay. Whereas if M does not halt on W, then this simulation never ends. It does never end. And if it never ends, and irrespective of whether K accepts V or not, halts on V or not, or whatever, M never gets a chance to come here and start the simulation of K on V. And therefore, if M does not halt on W, whatever that V is, it is implicitly rejected. That is, in this case, the language of N is the empty set. Okay. And there you recall, L satisfies property P and the empty set phi does not satisfy property F. So this is Rice's theorem, part 1. Any non-trivial property. Look at this. So we have made a very good use of this non-trivialness thing here. Yeah. This P of phi is F. There must be some L such that P of L is T. Or it's other way around, T or F. Okay. So in particular whatever examples we have seen, these are all non-examples. So giving a Turing machine and asking whether the language of the Turing machine is finite, this is not a decidable problem. Likewise, if you are given some Turing machine and you are asking whether its language is regular, or whether its language is context free, or whether its language is recursive, these are all properties that are, these are all, I would say, problems that are undecidable. Likewise, whether some Turing machine accepts any particular fixed string, that is again an undecidable property, undecidable problem. Whether a Turing machine accepts everything, that is again an undecidable problem. So we cannot build any total Turing machine for solving this problem. We will soon see in Rice's theorem part 2 that some of these languages are not even recursively enumerable. There we will use monotone properties. Okay, so I will come back to you once again after a small break. So see you again.